Homework 4.1, Exponential Functions, Video 2. Homework due Friday, May 29th at 11:59 p.m. Again, I don't have any specific homework questions that this video is associated with because these are general rules that can appear in any homework problem. Not just in this homework, but in future homework problems. And I guarantee you some of them will occur when you least expect them. When most books or teachers teach exponent rules, they usually just list a bunch of letters and symbols and stuff and say, here's what this means and everything. If we were meeting face to face, I would guide you through telling me these rules instead of me telling you by setting up specific examples and picking your brains. But the way I've decided to organize these exponent rules is a little more descriptively, because rules basically tell you when you can or cannot do something. So for these exponent rules, we're going to view them, for the most part, as when to do things, the two exceptions being here. For example, when do you add exponents? I think a lot of you know that and we've seen this already, that when we did something like x squared times x to the third, that's the time to add exponents. Because x squared means x times x to the third means x times x times x. If you glue these two multiplication problems together with another multiplication, then you're just counting how many x's there are total. So 2x's multiplied by 3x's is a total of multiplying 5x's. So how can we summarize this? Well, to represent the bases on these, I'm going to use b. And for the exponents, I can use anything that I want. We'll use an x and a y. So when to add exponents is when you're multiplying one power times another, but the powers have the same bases. The exponents may or may not be the same, so we need to represent them differently. But if you multiply two bases that match, then you can add the exponents. You could actually write out that whole sentence. If you multiply two matching bases, then you can add their exponents. When do we subtract exponents? Well, we've seen this also. For example, when we were doing long division and setting up some fractions, we would often set up something like this: x to the third over x to the second. And I just kind of casually reminded you that when you have one power on top of another with matching bases, or one power on top of another with matching bases, then you subtract the exponents. The reason's real simple. If you spread out all the x's, since everything's part of the multiplication problem, it's eligible to cancel in the fraction. So you had 3 x's and you took away 2 of them. If we want to write that generically, using b for base, then we need to set up two bases on top of each other and represent the exponents with different letters. So we'll say b to the x power divided by b to the y power. And along the same reasoning, if we were to write them all out, we would cancel, and so the amount left would be the top power minus the bottom power. So b to the x minus y. Now there are actually instances where we couldn't write them all out if the exponents were fractions, which we'll talk about here. But when you have one power on top of another, you can always subtract the exponents. When do you multiply exponents? I think when we were discussing end behavior of polynomial functions and we're looking for the leading term of a polynomial that was already factored, this rule kind of snuck in. If you have one power, say x to the third power, raised to another power, say to the second power, well, this literally means x times x times x squared. But that means x times x times x times x times x times x. So we have 3 x's 2 times for a total of 6 x's. So we can multiply them. So the time to multiply exponents is not when you have 2 bases, but one base that's raised to a power, we'll say the x power, and then that as collectively is raised to another power, we'll say the y power, and you get b to the x times y. That one looks intuitive because it looks like these should be multiplied and you would be correct. Now for the weird one, when to divide exponents. Well, I'm going to start this one with the end in mind, where when is it that we take one power and divide it by another? And we'll write that division problem as a fraction. Well, this one is one of them that's not so familiar. So I'm going to set up a numerical example and then we'll go fill in the left side of that rule. Let's say you have 25 to the 3/2 power. What does this actually mean? Well, without spending a whole lot of time developing how to attack this, I'll just tell you. When you raise something to a fraction power, the bottom of the fraction, the denominator, serves as an index on a radical. So in this case, a 2 would mean a square root. And the numerator actually serves as a power. So you could say 25 to the square root of 25 to the 3rd power. Now, what it doesn't say is which one you have to do first. The way it's written, it looks like you would have to raise 25 to the 3rd power and then square root that answer. But you could do the square root first and then raise the result to the 3rd power. Either way that you work it, it's going to be 125. You don't believe me, get out a calculator and check it. So maybe instead of writing this rule with the division of the exponents as the conclusion, I should write it as the division of the exponents as the beginning. So what does it mean to raise something to a fraction power, or a power that's a division problem? Well, the bottom number of the fraction tells you the index on a radical. So the y root, if you will. Whereas the numerator is actually an exponent. And you can either put the exponent inside and do it first, or you can do the radical first and put the exponent on the outside, either way. Now, so that one takes a little getting used to, but it's not really that bad. The hardest part is actually evaluating the radical, because if you had something like, I don't know, 32 to the 4/5 power, which is the 5th root of 32 to the 4th power, you might be thinking, and I'm going to do a thought cloud down here, what does this even mean? What does it mean to take the 5th root of 32? Well, that means you're looking for a number raised to the 5th power to give 32. So it's like square roots, but you check it with a different power, a power that matches the index. By the way, the 5th root of 32 is 2, and the answer to this is 16. So it's a little tricky sometimes to evaluate the radical when it's more than just a square root or a cube root. But if you understand what it means to be the answer to a radical, like the answer to the 5th root of 32 is the number that you raise to the 5th power to get 32, then at least you have a fighting chance of unearthing that number. Also, this rule is the reason why in exponential functions we don't let the base be negative. Why? Because if the base were negative, it could land under a square root and create imaginary numbers. And although that's a thing, it's a thing that's beyond the scope of what we're discussing right now. In other words, functions with imaginary inputs and outputs, for the most part, we stay away from in this class. There are classes that handle it. But this exponent rule is the reason why we're not letting negative exponents, negative bases in. How far is this video going? I'm not even at 10 minutes yet. We're doing good. Negative exponents. Well, this one kind of speaks for itself. What does it mean to take a base and raise it to a negative exponent? The rule for raising a base to a negative power is you take the reciprocal, so 1 over, the base to the positive power. So for example, if I ask you what is 8 to the negative 2 power, that negative means to take the reciprocal of 8 to the 2nd power. So it's 1 over 64. This is the reason the exponent can't be 0. Excuse me, this is the reason the base can't be 0. in an exponential function, because if the base were 0, it could get reciprocated and give us something that's undefined. So no negative bases, because this could create imaginary numbers. No 0 bases, because this could make it undefined. And by the way, the reason the base is never 1 in an exponential function, I know I'm going off on a tangent here, but the reason in an exponential function the base is never 1 is, what is 1 to any power? 1. It's a constant function. It always gives out the value of 1. So technically that is an exponential function, but its graph is a horizontal line and doesn't behave like other exponential functions. We'll look at the graphs of these in a little bit. 0 exponents. What does it mean to raise a base to the 0 power? For example, what does it mean to raise 8 to the 0 power? Intuition usually says the answer is 0, except that's not correct. You could ask your calculator and it will tell you a different answer. It's actually equal to 1. Now, how can I justify that anything to the 0 power is equal to 1? Well, there's a technical reason that's beyond the scope of this course, but I can give you a convincing argument. What if I give you 8 to the 5th power divided by 8 to the 5th power? Isn't that equal to 1? Yeah, same thing on both sides. But according to the second rule, that's the time to subtract exponents. So 5 minus 5 is 0. So the only way this rule can work all the time is if anything to the 0 power is 1. There's a better reason, but it's a little beyond what we can discuss. There is a stipulation here, except 0. 0 to the 0 power is called indeterminate. It's not the same as undefined. Undefined, you can't give it a value. 0 to the 0 power is indeterminate because in calculus, this can actually equal anything depending upon how you approach the zeros, similar to approaching an asymptote. If you're going down the calculus path, well, you're all on the calculus path. If you get to calculus, eventually you'll see about indeterminate forms and how they can actually equal anything depending upon how you approach that value. But for our purposes, we won't raise 0 to the 0 power. We can just call it indeterminate or undefined if you want to. When to distribute exponents? There's 2 distributive property rules for exponents. Rule number 1, if you multiply 2 bases, so we'll say a times b, and raise that product to a power, then you can distribute the power to each factor. So you can distribute a power across a multiplication problem, and you can also distribute a power across a division problem. So if you have a fraction with a power on it, you can give the power to each half. So those are when you can. Now, most teachers will stop here, but they should tell you, by the way, here's the ones you're not supposed to do. If you have an addition problem raised to a power, you cannot distribute. It would be nice if we could, but everything would fall apart, trust me. And the same thing with subtraction. You cannot distribute a power across a subtraction problem. I see this all the time at all levels of math. Stop. There is a gimmick for remembering when you can and can't distribute. I think I've shared this with you before, but it has to do with the order of operations. Please excuse my dear Aunt Sally. Remember, multiplication and division have the same precedence as do addition and subtraction, which is why they're on the same line. The rule for distributing in general is that you can only distribute across the thing below it. So I can distribute exponents across both of these, but I can't skip a level. I can't distribute exponents across addition and subtraction. So we're going to be seeing these rules quite a bit throughout the rest of this chapter. So if you ever forget any of them, feel free to come back to this video and get a quick review.